well, this wasn't. I should say testing, testing, testing. Okay, so let's go on with these simple introductory things. Okay, so I was here. Okay, so I've spoken briefly about. I wasn't there. I was here. Okay, speaking briefly about the continual need for bound states and how to choose geometries and whatever these bound states to be consistent with simple mean field ideas, etc. And so another one of our inputs is clearly these description of these systems at higher energy, so complex optical potentials. The battery's going, do you think, Marek? Can anybody see this? Yeah. I think the batteries are on the way out. Okay, so this discussion of distorted waves. Okay, so say my notation for this is chi. I don't think we've sufficiently coordinated within the lecturers that a distorted wave will always be chi, but I hope you know what I mean. So I say the distinctive thing about distorted waves is that we need an imaginary part in the interaction to take into account the more complex things that are going on in this higher energy collision. Okay, so what I've done is put in 3 slides here, which you're welcome to go away and look at afterwards, because Philomena will be introducing the effective interaction and the optical potential. And a standard way of doing it, some of you will be familiar, is a technique due to Feshbach, which is a mathematical decomposition. One doesn't calculate this per se, but it's a very nice formal way of understanding the different processes that are going on and identifying what we mean by an effective interaction takes into account other processes that are going on. Okay, so the whole idea here, let me just say a couple of words about this transparency, then I'll skip the next 2, which are just the algebra that follows this. Okay, but the idea of the Feshbach approach is that we've got two bodies that are colliding, and for instance, if we're interested in elastic scattering, then there's a part of the wave function for this complete system that describes elastic scattering, but then there's a whole load of other things going up in elastic scattering and breakup and all sorts of other processes which contribute other pieces of the wave function. And I say the notation of Feshbach puts all that other complicated stuff into some inelastic piece of the wave function. So there's the elastic piece, there is everything else, and you set up a mathematical apparatus that says there is a projection operator P, which when it acts on the full wave function pulls out the elastic part. And there's another operator Q, and when Q operates on the total wave function, it pulls out the rest. Okay? And then one can do an algebra with these P's and Q's. Because they're defined as projection operators, then it means that P and Q, or Q on P gives 0. P plus Q is everything, because you sum back the full wave function, etc. Okay, so there's a simple algebra involving these operators that allow us then to look at the Schrödinger equation and divide it up into various pieces. Okay, so I'm not going to go through that, but to say there's 2 slides following this, which you're perfectly well, you can pull down the lecture notes and look at them yourself, but let me not tread on the toes of those who are following behind. Okay, so this is a way of formally showing that the optical potential is complex. There's an imaginary piece. This is it pictorially. Okay, don't worry about the formulae, but this is the picture. There's an elastic scattering wave function. It couples to this inelastic piece, and the inelastic piece can couple back. And I say it's the nature of this two-way coupling and what it does to the Hamiltonian, the interactions here that matters, and what the algebra is allowing you to do. Okay, so the important thing is that the potential gains an imaginary part. Okay, so I say, I don't know if people have been through this exercise. What is on the left here is the sort of thing you all do in your undergraduate quantum mechanics, right? When a particle moves in a constant potential field, there is a wave number, and then the wave function in one dimension looks like a plane wave representing particles traveling to the right with a definite momentum. Okay? So I don't know if people have done the corresponding problem where instead of moving in a constant potential which is real, if you move in a constant potential which is both attractive, negative sign, and imaginary, then you can do the same algebra, but of course then you have to take a different square root here involving an imaginary piece, and the wave number there then becomes complex. Okay, so if you haven't worked through this exercise before, you might like to do so, and if you assume first of all that this potential V naught is strong and that imaginary piece is relatively weak, then when you take this square root here, you can use the binomial theorem. So you get something like this, and you would take the first term in the binomial theorem, and then you can convince yourself very easily that this k bar, this wave number that sits in this thing here, has a real part, which is exactly the same as you had over there. Then it gains an imaginary part here, which is positive. Okay? If that potential is attractive, then that ki there is a positive number, and so when you put this into here, that positive imaginary part means that this wave function here, travelling to the right, looks like a momentum eigenstate, but this momentum eigenstate decays away with space with a decay constant which is proportional to this imaginary piece of the wave number. Okay, so what I'm trying to remind you here is what the role of an imaginary part is that it takes a wave function and it absorbs it away. The wave function decays away, and so what we're doing is losing flux from this wave function as this imaginary part takes the particles and puts them somewhere else. Okay, so as I say, if you haven't gone through this exercise and you are unsure about why an imaginary piece or what the imaginary piece does, that's what it does. Okay? When a wave function propagates into an imaginary potential, it decays away exponentially. Okay, so let's continue and go to thinking more about the solutions of these different two-body problems and what they look like at large distances. Okay? In particular, the scattering wave functions at large distances, as I said, they connect with the observables, with the measurements, and so they tell us the real connection between experiment and the interactions that we're using. Okay, so as you'll probably know, and if you don't know, you'll certainly get it in the next day or two. What we're actually needing to do when we solve a two-body problem such as this is solve a three-dimensional Schrödinger equation. We need to go into a centre of mass coordinate system, which brings reduced masses and such like. And the way we solve such a problem is to break it down and consider, as I've said, let's consider what is happening in a particular set of angular momenta. The wave function for such a set of angular momenta is what we've written now several times already. And that means we have to solve a Schrödinger equation at a radial level. Okay, so this is where the physics is. Everything else is padding. Everything else is fluff. Okay? Spherical harmonics, Clebsch-Gordon coefficients, sums over the appropriate z components, but the physics is in solving these radial equations here. Okay, so what we need to do is be able to solve lots and lots of radial equations with the right boundary conditions according to the problem we want to solve. Okay, so whatever we solve, whether it's bound or continuum, we need to solve this radial equation. For bound states, of course, the energy is negative, and for scattering states, the energy in the central mass frame is positive. Okay. Okay, so again, when you run codes, for those of you who've done DWBA calculations and other reaction calculations, you will know that a code will ask you lots of questions about how you want this potential to be chosen. Okay, so you'll have to tell it the geometry of the real part of the potential. You'll have to tell it parameters that control the geometry of the spin orbit potential. And there's even more parameters for the imaginary piece, because normally you have the option, or you need to use both a volume piece, which follows the density of the nucleus, and a derivative piece, which is surface peaked. Okay, so these are conventions, but in order to run a calculation where this is the interaction, you need to specify the optical potential, and so there's a number of parameters which we need to define, and we have to get them from somewhere, and that'll be discussed as we go along. Okay. Okay, so let me remind you again of some obvious things. So we need to solve the Schrödinger equation. Here's our radial equation. If we can solve this, we can do most of reaction theory. Okay? One-dimensional differential equations is ultimately what most of the time is involved in solving in reaction theory. And so for bound states, let me remind you, the energy is negative. Okay, so when you put in a negative energy, you end up with an equation just like this, and it'll be as no surprise to you from your undergraduate quantum mechanics that if you look for bound states in a potential which confines the particles to some distance, the spectrum will be discrete. You'll get a set of allowed energy levels within the potential well, and only for certain values of kappa beta, only for certain values of energy will you obtain solutions of this equation which have the right physical boundary conditions for a bound state. Okay. On the other hand, for scattering states where the energy is positive, the differential equation is the same, except that the sign of this term has changed. And of course, once you become unbound, the spectrum is continuous. Okay? There is a solution possible for any value of k, and so there is an infinite number of solutions of this Schrödinger equation, one for each energy in the continuum. And therein lies the difficulty later on when Antonio and others start to discuss breakup, where you start out with the system in a bound state and you excite the system to the continuum. There is an infinite number of final states, and infinity is never a good idea when you're doing calculations. Okay? So somehow we have to try and turn this infinite set of solutions, one for every energy, into a finite set of solutions which encompass the important physics of this infinite set. Okay? And continuum bins, for instance, where you say, this block of energies are all rather similar, surely I can treat this as this infinite set as a representative sample of what is happening in this particular energy interval. So we'll talk about that a bit later if I don't run out of time this morning. Okay, so bound states, a couple of bits of nomenclature we should use. Again, there's the radial Schrödinger equation. Once you go outside the range of the nuclear forces, if it's a neutron, then the potential will disappear altogether. If it's a charged particle that you're talking about here, then outside the range of the nuclear force, the only thing you're left with at large distances is the Coulomb force, in which case you continue to have this 1/r potential representing the long-range Coulomb interaction. Okay? But this solution, the solution of this equation, either with the Coulomb interaction, this term, or without it, in which case you strike it out. Those are well-known solutions of the Schrödinger equation. They're a standard set of functions. Okay? In the case that the Coulomb force is present, it's called a Whittaker function, and you can look it up in your favorite handbook of mathematical functions. Basically, it decays away exponentially at large distances. So, as you would expect for a bound state, outside the well, the solution must decay exponentially at large distances. Okay? If the Coulomb force is not there and that term is there, then this is even simpler. It's not a Whittaker function, it's a Hankel function, but that's neither here nor there, really. It also decays exponentially at very large distances. Okay? So the reason for mentioning this is to introduce the words asymptotic normalization coefficient, because I say this normalization of the wave function at large distances is very often the only thing you need to know if you're doing reactions at very low energy for astrophysical purposes. You bring nuclei together at very low energy, then only the extreme tails of the system interact with each other. And out there at large distances, this function is known. The only thing you don't know is that number, which is what to scale the wave function by. And so in low energy experiments, knowing this number, which tells you the magnitude of the wave function at large distances, is rather important for figuring out nuclear reaction rates for astrophysical purposes. Okay? It's a challenge to measure these things, but there are techniques to do that. Okay, so my reason for going through this at this level of detail is to introduce you to the idea that there is this thing, the tail of wave functions of a well-determined radial form, functional form. What we don't know until we calculate it is what the number is that tells you the normalization of that. And it's more than simply an inconvenience. You actually need that number with some accuracy in order to determine reaction rates at low energy of an astrophysical type, for instance. Okay, so let me remind you about our phase shifts. Okay, so because scattering solutions, it's a large distance behavior that determines what you actually measure in detectors at infinity. So when we solve the scattering problem, we solve this radial equation for positive energies. Then once again, as you will know, if I go to large distances and outside the range of the nuclear forces, then the only thing I'm left with is an equation with a Coulomb interaction in, or if it's neutral particles, I won't even have that term there. Okay? So let me remind you from scattering theory, and if you don't remember, you'll get reminded of this in the next day or two. The solution of this equation at large distances, i.e. what the scattering solution looks like at large distances at a given energy, is some linear combination of a regular solution and an irregular solution of this homogeneous second-order differential equation. Okay? If the Coulomb force is there, once again, you can look up in your favorite book of mathematical functions what the solutions of this differential equation are. They're usually called f and g. F is like a sine, g is like a cosine. Okay? So this one goes to 0 at the origin. This one does not go to 0 at the origin. So essentially at very large distances, this one looks sine-like, this one looks cosine-like. They're very simple functions. They just oscillate, showing that they're waves. Okay? And the additional thing in terms of in these known functions is that we have a phase shift which contains all the information about the fact that at short distances we had this potential operating, and so at large distances the wave has a distinctive phase, and that is called the phase shift delta. Okay? Now so there is an exercise this afternoon, pen and paper, not computer, to ask you to remind yourself of if you've got these asymptotic boundary conditions for a scattering wave. There are various ways you can play with sines and cosines. There are various forms in which you can write this asymptotic solution. Okay? Two conventional ones are what I've got here. Okay? One is writing it in terms of sine and cosine of the phase shift. Another one is in this form. This is exactly the same as this, but you've just used some trigonometric identities for the sine and the cosine. Okay? So this is more often used, and this is called the S-matrix form. Okay? And physically it's rather more obvious than looking at this one, in the sense that this combination, remember I said this is basically a cosine, and this is basically a sine, right? And so this combination, cosine plus I sine, or cos plus I sine, that would normally be a complex exponential function. Okay, so by taking this linear combination, instead of talking about cosines and sines, what we've got are exponential functions e to the I kr, and so this combination here represents waves that are coming into the collision, and this combination here, h plus, represents waves that are scattered and going out after the collision has taken place. Okay, and you can see in this form there's a 1 multiplying this, so the incoming waves come in with unit magnitude, and the outgoing waves go out with some amplitude determined by S, and S is called the S partial wave S matrix element, and it tells us the amplitude of these outgoing waves. Okay? So that's going to tell you how many particles end up reaching the detector. Okay? Because this is the outgoing waves. Those are the things that are now free to go out. And this amplitude here ultimately is connected with the cross-section and the things you measure at the detector. Okay? So this is S matrix form, and as I say, there's a pen and paper exercise this afternoon to ask you to play with these equations just to remind yourself of what is going on there. Okay, so I think I've said that. Okay, so this is the reminder side. So this is the wave function at large distances, ingoing waves with unit magnitude, outgoing waves, and with that amplitude. Okay, and you can see that this in general is a complex number. It's an amplitude, a quantum mechanical amplitude. So in general, it's complex. This is the relationship of that number to the phase shift. Okay, so if you've got the phase shift, you've got S. They're telling you the same information. And the modulus squared of this amplitude, when you take modulus squared in quantum mechanics, you get a number, a real number, which is telling you something about probabilities, right? So this guy squared tells me the probability that there are outgoing waves in the collision. That is, the particles have come in, and there's a probability that they're coming out. So this is the survival probability and the scattering. And this combination, therefore, the total probability must be 1. So this combination of things here is the probability that in the scattering the particle has been absorbed. Okay, so calculating these quantities S has a direct correspondence that for scattering with this set of quantum numbers, with this orbital angular momentum, this is the survival probability, and that is the probability that the particles have been absorbed by the complex part of the optical potential in this scattering in that partial waves. Okay? And as I said down here, once you've got that number, once you've got that set of complex numbers, you can complete all the scattering observables at a given energy and for this potential. Okay? But other people will deal with the observables. I'm just at this point interested in us calculating some of these things and understanding what they look like so that when you do a more complete calculation later on, you'll understand when this thing is mentioned, you'll have some idea what it's telling us of the physics of the situation. Okay? So this is the reminder of what a phase shift is. Okay? So say some of you will have done a lot of scattering theory, some of you will have done very little scattering theory, particularly if your primary interest is in nuclear structure or designing detectors. You may not have thought about phase shifts in a little while. Okay, so let me just remind you what the phase shift basically is if there's no potential, your scattering solution looks like a well-defined oscillatory wave. If you have an attractive potential at short distances, that sucks in the particles. Particles like to be in regions of attractive potentials. The wave function gets pulled in, and if the wave function gets pulled in, that's a positive phase shift, and as you see, relative to this one above, this guy has been moved. That maximum is now moved there. Okay, so that's the role of an attractive potential. Please come and join us, and pulls the wave function in. On the other hand, if the potential at short distance is repulsive, the wave function does not like to be of any size there, so the wave function gets pushed outward, and then the peak here will be moved in an outward direction, and that phase shift is defined as a negative phase shift. Okay, so what the potential at short distances is doing to the wave function is very simple. It's either gathering it in or pushing it away, and I say the phase shift is not telling us anything more significant than just the extent to which the wave function is being shifted inward or shifted outward by the presence of this interaction at short distances. Okay, and so that's, if you prefer pictures to a formulae, that's what we've got. Okay, that's the formula. If you don't like the formula, what we've got a scattering situation. So at some energy, we have instant waves of unit magnitude, which is this form, and we have a certain probability amplitude that will end up with outgoing waves at the same energy here in elastic scattering, for instance, and the amplitude of those is given by given by S. Okay? This translates into a probability that we find waves out here, and it translates into a probability of this, that the flux gets trapped in this short distance by this imaginary potential over here, absorbing the wave function as we saw earlier, decaying the wave function away, and reducing the probability of survival. Okay, so next week, so looking ahead, if you understand what this S matrix is telling us then, what we've seen is that at short distances, small angular momenta, which mean head-on collision, effectively. Okay, that's when angular momentum is small. Let's just remind ourselves, if I've got a particle coming in with some momentum, k, at some impact parameter b, then L, the orbital angular momentum, is essentially the momentum k times b. Okay? And so the angular momentum is small when b is small, and so that means head-on collisions. Okay? So when the angular momentum is small, this and this come together head-on, and the likelihood is that the collision will be a violent one. It'll be strongly affected by the imaginary part of the potential, and this sort of trajectory will be strongly absorbed, and so the modulus of this S matrix element will be small, reflecting the fact that there's a very small probability that this object will survive the collision in a head-on collision and emerge the other side. Okay? But then eventually as B increases, which means increasing angular momentum of the system, we get to a point where B is such that these two nuclei just graze at the nuclear surface, and at that point the probability of survival goes up dramatically, and eventually B gets sufficiently big that these things really don't interact at all, in which case S will be entirely 1. Okay, so the general form of the modulus of S here is something which is absorbed at short distances and goes to 1 at large distances. Okay, and this angular momentum here is typically something like k times the sum of the radii of these two objects, is where the surfaces cease to touch and the survival probability becomes essentially unity. Okay. Now, what this slide is supposed to show in addition to that is that if the energy is high, such lots of L's happening, or if these are heavy ions, such that K is big, then there'll be many orbital angular momentum involved. Okay, and I've tried to represent this by putting all these red dots here, showing you that many angular momenta are involved in such a collision at high energy, or with heavy ions where you carry in lots of momentum, and so lots of L. And all I'm trying to show here is that in the case where you've got lots of L and lots of points like this, then it's perfectly reasonable to draw a smooth line through those points, which is what the black line is supposed to represent. It's not clearly the right line, but if you're in these regimes where you're at higher energy or large numbers of angular momenta, very often we can draw a smooth curve and then deal with the smooth curve in terms of the discrete points, and that leads us into the realm of semi-classical approximations, where instead of talking about L, we talk about B as a continuous variable, the impact parameter here, instead of the discrete index L. Okay, so we're not going to talk about that today, but next week we'll talk about semi-classical approximations. And what we're really doing when we talk about semi-classical approximations is recognizing the fact that these absorptive properties in the interaction vary smoothly with orbital angular momentum and with impact parameter. Okay, so let's say a few words about resonances, okay? So another aspect which I'm going to ask you to think about this afternoon, the algebra a little bit, is low energy collisions. Let's see. So if we're talking about low energy collisions, it really means we have very little kinetic energy available, and so we have essentially no energy to excite, target, or excite objects. So the potentials essentially are real. There's no imaginary pieces kicking around because there's not sufficient energy to do any significant excitations. Okay? And a feature when you scatter light systems together at low energies is that the density of excited states is rather small. You're in regions of low level density. Okay? And what I've drawn here is an example which towards later in the course when you discuss the R matrix with Pierre Descouvement and with Ed, this is one example you will do where you will look at the alpha plus carbon-12 system or nitrogen-15 plus proton system and look at the cross-sections for this system which have interesting resonance structure as you change the energy. Okay, so if you scatter an alpha plus from carbon-12 at very low energies in their centre of mass frame, what you can see is that you come into the system of oxygen-16. That combination of nucleons produces oxygen-16, and depending on the energy that you come in at, you will strongly couple or not to some resonance structure in the compound system. Okay, so a common feature of scattering at these low energies is resonant behavior in the cross sections you measure. Okay, and as I say, you'll get really stuck into that and look at these data and understand what you need to do to fit those later on in the course. Okay, but what's going on there from the language that we've just been talking about potentials and S matrices and things, is that if you've got a system where you've got some nuclear potential at short distances, as we've been describing, and we've got systems which have some angular momentum, and that means they've got a centrifugal barrier that looks like this. Okay? If you look in your radial differential equation for your Schrödinger equation, you have this combination of stuff. Okay? And this is repulsive and gets bigger as you go to the origin. Okay? And this guy is attractive. And if you add these two together for some reasonable energies and angular momenta, you find you get pockets in the potential. Okay? This one wants to be repulsive and go up, but this one wants to pull it down and attractive. So you get some pockets. Okay? And you know that when you have things like this, we'll call them potential barriers, and then quantum mechanics would let you tunnel through this potential barrier. And so you can see I've drawn a line here. So say you were scattering particles at this energy with this angular momentum. You will see that the particle will come in, it will encounter this barrier. There's a probability that it will tunnel through the barrier and get trapped inside for a while, and it may tunnel back out or it may not. Okay, but this is the origin of resonance structure that you'll see in potential models of the sort that we're describing here. Okay, whenever you have a barrier, an attractive potential and a repulsive potential, you have the capability to have a resonance because you'll have a pocket like this in which the particle can get trapped for some time. And you will know that there's a relationship between the time degree of freedom and the energy through the uncertainty principle. Okay, so another thing we really should think a little bit about is how to recognize these resonance structures, because if a system has a well-known resonance, our potentials we use should reproduce the position of known resonances in the structure. Okay, so how do we describe such resonances? Okay, well, we'll talk. I say there's an example for you to look at this afternoon, but what I've already hinted earlier on is that the signal that we have a resonance situation is in these phase shifts that we were talking about before. Okay, the potential shifts the wave function in and out, and the signal of a resonance, I think it's clear on the next slide, is that the phase shift rises through 90 degrees. Okay, why? Well, we think about that this afternoon, and we can think about it on the next slide. Okay, so the key message from here is if there's repulsion and attraction, so the repulsion can come from this centrifugal barrier, but another way of getting repulsion is from the Coulomb interaction. Okay, if I have a proton at low energy with no angular momentum, then this term will be absent. Okay, and so you won't have this barrier here if there's no angular momentum. Okay, however, you can also get repulsion from a Coulomb interaction. Okay, so the combination of a proton at low energy, even if L is equal to naught, I'd have to add a Coulomb, well, the Coulomb interaction will be in here, so I can still get a resonance and a pocket for a proton with no angular momentum, because there is still the capability to have this. Okay, what you'll see is that if I've got no angular momentum and no Coulomb interaction, so I have a neutron in a low energy S wave, I will not get a pocket. Okay? So I won't get a resonance in this sense. Something else may happen, but we won't get a resonance in the sense that I'm talking about here, with potential pockets affecting the phase shift you see in the low energy continuum of this system. Okay, so let's say this is the sort of thing that I'm going to ask you to think about this afternoon. Okay, how, if I've got this S matrix, which is telling me about the amplitude of the outgoing waves, how do I introduce into this language the idea of resonances? Okay, and if I do have a resonance in a particular angular momentum state, let's call it L now, to pull it out from the mass of other L's. If in a certain angular momentum state there is a pocket and the energy is just right to set up some sort of resonance, then in general the resonance will do something which changes rapidly with centre of mass energy, but there might be bits of the phase shift due to other things, average potentials or other couplings, which just produce some smoothly varying piece. So the idea of this is that the phase shift can have a rapidly varying piece due to some resonance structure, and some more slowly varying piece, which we call a background phase, due to other stuff that's going on. Okay, and the standard way of parameterizing this bit, if we have a resonance, is that we describe this resonant phase using a formula that looks like this. Okay, now I don't expect you to take this in sitting here as to what this means, but if you look at this in the cool of day, you'll see that this formula says that as you change the energy, the centre of mass energy of the system, this describes a situation where as you change the energy and increase it, as you get near the resonant energy, the phase suddenly changes from something being small, passes through 90 degrees, and becomes something large. Okay? And this gamma in there tells you how quickly it takes you to go from a small phase shift to a large phase shift. Okay? So this simple parameterization parameterizes the system where the resonant phase passes through 90 degrees with a width for that change. Okay, and what you can show, and this is the exercise, I'm not going to spend very much time doing it here, is that if you parameterize the resonant phase shift in that way, then what you get is the contribution of this resonant partial wave L to the cross-section for elastic scattering, say, involves the sine squared of the phase shift, and this little bit of algebra will show you that the cross-section has this form here. Okay, and this is called a Breit-Wigner shape. Okay, and this is the peak. The cross-section will have a peak. It'll go up and it'll come down over a distance of something like gamma, and will reveal the fact that in the scattering in this particular partial wave, the phase shift is doing something interesting. There's a rapid variation showing you the presence of a resonant structure. Okay, so as I say, this will be important later on to have an idea of how you can spot a resonance in the potential two-body system such as we're talking about. And we can see that this afternoon by looking at the phase shift, seeing phase shifts that change through 90 degrees, and also doing a little bit of algebra with this thing. Okay. Now you'll remember there was a rapidly varying piece of the phase shift, which I called delta resonance, and then I said there was this background piece, this one. Okay, so what you will actually see in an experiment, if you've got a resonance, will depend on interference between this resonant piece and what else is going on at the same time as the resonance. Okay, so this is taken from the book, which I'm sure probably Philomena will use this later on as well. But this is just supposed to show you if you've got a phase shift which is going through 90 degrees, and then you add on to it various backgrounds. So assume the background phase is pi by 4, or pi by 2, or 3 pi by 2. Okay, so the phase shift's going from 0 through 90 degrees, and then you add on the background, so it looks like this. What this will predict as a resonance seen in the cross-section will be rather different in shape. Okay, so this is if the background pole was 0. That's your standard looking bright Wigner shape. That's the thing you probably would call a resonance from stuff that you have done before. But the shape of this, what you actually see in the cross-section, whether it's a peak or a dip, is telling you something about the background phase shift, which is interfering with the resonant phase shift. Okay, so we will test some of these things later on. Okay, so this is this I asked you to show this afternoon. Okay, if the phase shift is doing that, which is what I said, if this is a way of parameterizing the phase shift for the resonant piece, what does it mean for the S matrix? And say, for some of you, this must look rather horrendous, but this leads naturally to this when you think about what the definition of the S matrix is as e to the 2I delta, the phase shift. This is this. Okay, and this introduces us to another sort of notation, another sort of language, because if you look at this, what's in the box, you'll see that what's downstairs there has the capability to be 0. Okay? If I go to an energy, centre of mass energy, which is imaginary, God forbid, wind up your accelerator so that you have a real energy and an imaginary piece to the energy as well. Okay? But you'll see that mathematically, this denominator can vanish if the centre of mass energy is resonance energy minus I gamma over 2. Now that's a complex value, and so what that says is that this S matrix has a mathematical pole. That's what happens when you get something downstairs which can vanish. You call it a pole in a mathematical sense. And I say I'm mentioning it here, and not because we're going to take this particularly forward, but if you can identify mathematical structures with these resonances such that a resonance is a pole in the S matrix, that takes you to another sort of formal apparatus that you can use to do analysis of such systems, okay, and refer you to the textbook. Okay, but deriving this is rather straightforward from this, and I ask you to think about that this afternoon. And if your trigonometry is rusty, it'll help make it a little less rusty. Give you a bit of metal polish to get it up and shining again. Okay, so this is for tomorrow, really. Okay, I've been talking happily about bound states. Okay, I've been talking about how we can calculate bound states of nucleons in nuclei by looking at finding out what the appropriate quantum numbers are. I talked about oxygen 24, the last neutron being in a 2s1/2 state. You can look up its binding energy from the literature experimentally, and you can calculate a bound state. Okay, and so I've got this idea so far that we have these normalized bound states for two particles, looking like this. Okay, of course, not quite so simple as that. It's almost as simple as that, but not quite so simple as that, because when we're talking about taking neutron out of oxygen 24, what we're really talking about is a 24-body problem. And I take one neutron out and I'm left with a 23-body problem afterwards. Okay, so to what extent is that single particle wave function of two bodies, this bound state wave function, to what extent is that a good representation of the motion of this neutron within this 24-body problem, which is oxygen 24? Okay, and it can be, but that introduces us to the idea of overlap functions. Okay. Instead of this two-body normalized wave function, the correct language to use is that actually I start out with a nucleus Y, which has perhaps A nucleons in it, and I'm going to take a nucleon out, so I'm going to end up with a nucleus X, which has A minus 1 nucleons in it. Okay? And the real question we should be asking is how much does that nucleus with 24 nucleons look like that nucleus with 23 nucleons plus one extra nucleon in this in this state. Okay, so tomorrow we'll go in some detail talking about overlap functions, because that is the essential connection, or an essential connection between nuclear structure and many body wave functions before and after you've taken the nucleon out, and this wave function which we're trying to treat that complicated physics in terms of. Okay, so the language there, I'm sure you've gone to conferences, you've heard the words. The magic word is spectroscopic factors. Okay, the magical ingredient. You use your bound state and you make the whole world right by just multiplying it by a number, which is a spectroscopic factor. Okay, so tomorrow I think we need to discuss this issue, okay, and how we really can, if we're calculating this in a simple model, how can we relate it to this more complicated system here, okay? And tomorrow we'll talk about this formally, at least I will, and then Ed will show us how we can calculate some of these spectroscopic factors using one form of 24-body wave function, namely a shell model wave function, for instance. Okay. Now, I just want to show you here that what we're talking about is not nonsense. Okay, the idea of using a Wood-Saxon potential to generate this wave function for a nucleon moving in a many-body system is a good one if we can choose the parameters of the Wood-Saxon potential appropriately. Okay, because what I'm showing you here, and we're not going to do this detail of calculation at this meeting, certainly. Some of you will know that there's been an enormous effort over many years in the US at Argonne National Laboratory to actually calculate from first principles these many-body wave functions. Okay, and it's a massive task, but you can do it up to about mass 12. And what I've shown you here, an example, these dots on this curve are the radial overlap function, the bound state, if you like, of a proton with respect to lithium-8 in a 3+ state in beryllium-9, calculated from first principles. Okay? So we can ask the question, if I take a proton out of beryllium-9 and leave lithium-8 in a 3+ state, what does the wave function of that proton look like? Okay, that's the question. And that's what it looks like. Okay? So this proton must have been in a p3½ state. I think that's the only thing around this part of the nuclear chart that can couple 3½ minus to 3+. You must have 3½ minus to make that possible. Okay, so we're talking about a proton in a one p3². The 1 means it's the first p state. And if you remember, the first p state will not have any nodes, and this does not have any wiggles in it. Okay? And the dots, as I say, are the result of a very large calculation to work out that overlap. Okay? And what I want to show you here is that if you calculate that wave function using a Wood-Saxon potential, a simple potential model, choosing a radius parameter and a diffuseness parameter in a sensible way, then you get the red curve. Okay? So there is a microscopic calculation, and there is a very simple representation of that microscopic calculation in that Wood-Saxon wave function. Okay? If you can choose the parameters of the well correctly. Okay? And the other thing is, of course, that those dots, if you work out the normalization of those dots, you don't get 1. It's not a normalized bound state wave function. There is this thing called the spectroscopic factor, and in this case they calculate that spectroscopic factor to be the square root of that number there. Okay? So all I'm trying to show you is that when we're doing reaction theory, we can't dial up the solution of these wave functions. Okay? Normally we would say there's a bound state here. Oh, let's calculate it simply using a potential well. So what I'm saying to you is, how can we choose the values of that potential well to satisfy other information we know, be it from theory, or be it from experiment, or be it from a Hartree-Fock calculation? We should take the best information we have from whatever source and make sure the bound state wave functions we're using are consistent with other things that we know. okay, rather than using necessarily those numbers that we tattooed on our wrist earlier, okay, 1.25 and 0.7, 6 MeV spin orbit. They're a good start, but probably wouldn't give this. You'd have to do some fine-tuning on those parameters if you know that this is a better calculation of that bound state. Okay, the other thing we can do, and we will do tomorrow, is another way to get information about these overlaps is that one can use the shell model, for instance. Okay, so here's another example. Neon 26, so that's rather neutron-rich neon. Ground state is 0 plus. And if we look at neon 26, okay, I'm going to take a proton out. Okay, so it's neon has Z is equal to, you know about neon? God, gone to sleep again, need more caffeine. How many protons in neon? 10? Good. Okay, so we look at neon 26 and say, I want to take a proton out, so which proton am I likely to take out? And so there's the 8 protons that fill the S and the P shell, and then I've got put another 2 somewhere up here, okay? These are supposed to be lighter. Do they look lighter? I'm not saying there's 4 up there, there's 2 up there. They have to couple to 0 plus, so they've either got to be both in there, or both in there, okay? They must be in the same J state, because all these are paired up, so these must couple to spin 0. And so the last 2 nucleons must sit in either one of those 2 orbits, and they must both be in the same orbit. Okay, so what we would expect, probably, because of residual interactions and all sorts of complicated configuration mixing and all sorts of things, is that most of the time, probably, the 2 protons will sit in d5 halves, but a small amount of the time, they may spend a little bit of time in 2s a half, or 1d3 halves, depending on how big the gaps between those mean field states are. Okay, so all I'm going to show you is over here. Of course, in the shell model, you can calculate a wave function for 26. You can calculate a wave function for fluorine 25, which is what you get having removed a proton. And in general, there'll be several 5 half states when you put in the configuration mixing, etc. And so tomorrow, we hope you'll calculate things that look like something like this. You may not do this example, we do an example. And this shows us that there's the ground state. Okay, so we start out with, beg your pardon, we start out with, this is the ground state over here. Okay, so we, energy 0. So we start out with the ground state of neon 26, and then we ask what is the spectroscopic factor, which is S there, for taking out a d5 halves proton sitting over there. Okay, and here are the numbers, and you'll see that the big number here is about 1.8, and the rest of the numbers are pretty small. Okay, so this number seems to be telling us to say we'll discuss this tomorrow, but it's saying if I look at this overlap, what the shell model is telling us that most of the time we will find these 2 particles in d5 halves here, and the number is almost 2, but it's not 2. Okay, and there's an additional effect that goes in here, so which we'll discuss tomorrow. Okay, so another way of doing these overlaps, another way of choosing how do we choose our bound state correctly to be consistent with what we know structurally about this system, is to do a shell model calculation and ask the question, what number should I actually multiply the normalized single particle wave function by in order to correctly represent the strength that's in that d5 halves orbital, for instance, in this case. Okay, I think I'm going to pass on this because we're going to talk about this too tomorrow. Okay, or do I? Well, maybe I should. Maybe it won't be done in quite this way tomorrow. So, have I got the right time? What time you got, Marek? Quarter to 12. Okay. Okay, so I've talked a lot about neutrons and nucleons and oxygen 24 and what we just did, neon 26 or whatever. So we have some idea of how to choose the quantum numbers for nucleons that we want to knock out or transfer or deal with in those sort of systems. Also, we have to deal with clusters. Okay, so perhaps it's less obvious that, perhaps it's a little, less obvious how we do it in the case of clusters. Okay, so I'm going to take an example here, lithium-7. Okay, now lithium-7 is it's lithium, so it's got 3 protons and 4 neutrons. Okay, and lithium-7 is a system which is known to the low-lying states in lithium-7, just like lithium-6 that we showed before. Very few levels, and these are well described as being cluster states. Okay, the lithium-7 in its ground state looks a large fraction of the time like an alpha particle orbiting a triton and vice versa. Okay. And so if I need a wave function for this system, if I would want to do a reaction where I remove 3 neutrons out of lithium-7, then I'm going to need a bound state wave function for the motion of a triton relative to an alpha particle in lithium-7, for instance. Okay? And what quantum numbers should I use? Okay? Well, some of the quantum numbers are obvious. Because the ground state of lithium-7 is down here, it's 3/2 minus. Okay, and if I represent lithium-7, which is 3/2 minus as an alpha and a triton, the alpha particle has spin 0, and the triton has spin 1/2, and so it looks very much like the way I get a 1/2 minus state. A 3/2 minus state is that the two have relative orbital angular momentum 1, and spin 1/2 of the triton, that couples to 3/2 minus. Okay, so that's what it looks like. But what is n? How many nodes should this wave function between the triton and the alpha particle have? What is the principal quantum number that we should use in the case of a cluster? Okay. Now the way we normally do this is to use harmonic oscillator model and harmonic oscillator rules, because that's a very nice way of conserving energy, making sure you've got a cluster state that has the right energy, and that you don't violate the Pauli exclusion principle. Okay, so like I say, we're going to use the oscillator model also tomorrow. So let me just remind you of what the harmonic oscillator picture in 3 dimensions looks like. So here's our harmonic oscillator, well represented in 3 dimensions for neutrons and for protons. And we've got no spin orbit forces in here, okay? So this is just a central harmonic oscillator potential. And when you put particles into this harmonic oscillator, then just like for the Wood-Saxon well, the lowest energy states are rather similar. First you get an S state, the lowest S state, then you get a P state, then you get a degenerate 2S and a 1D state, okay? And I've drawn it here so you can see that nucleons that you put in this lower shell don't have any oscillator quanta of excitation associated with them. Particles that you put in this state each have h bar omega of excitation energy relative to this lower state, okay? And stuff that goes up there has 2 h bar omega if you need nucleons to put in there, okay? Now you'll see in this model for the lithium-7, you've got 4 neutrons, 3 protons, so you drop them in consistent with the Pauli principle, and you put 2 here and 2 here and 2 there and 1 there. And so this total configuration has 3 particles above this lowest level, and so lithium-7, when you apply the Pauli principle correctly, has 3 harmonic oscillator quanta of excitation, 3 h bar omega, okay? 1, 2, 3. Okay, and you can see if you look up here, this is the rule. Okay, I think you will see that if I take this number, whatever it is, take 1 from it, multiply by 2, and add the orbital angular momentum, I get the right number of quanta for the orbital. Okay, so for this one, L is 0 and N is 1, so that gives me 0. For this one, L is 1 and n is 1, so that gives me 0, and that's 1, so I get 1 h bar omega for there. Okay, so this is the oscillator rule that tells you how the principal quantum number and the orbital quantum number conspire to give you the number of oscillator quanta associated with that sort of single particle state. Okay, so when we want to think about the cluster configuration, then we want to write lithium-7 not in this shell model-like picture, but we want to write it in a cluster picture. So we must take our 7 nucleons, which in lithium-7 like this, and we distribute 4 of them into an alpha particle, so it look like that. Okay, and we put 3 of them into a triton, so that will look like that. They can all go into the lowest oscillator shells in these individual clusters. And you will see that this alpha particle, therefore, is associated with an intrinsic alpha particle state which has no oscillator quanta of excitation. And similarly, the triton here, all in the lowest level, so it's got 0 h bar omega of excitation. And so we started out with something with 3 h bar omega. The alpha and the T themselves contain no internal quanta, and so those 3 quanta of excitation must be involved with the relative motion of those two systems and not with the internal structure. Okay? So that allows us, given our rule that says that twice the number of nodes plus the orbital angular momentum tells me how many are oscillator quanta, the number of nodes associated with the relative motion of these two clusters and their orbital motion must be such that 2 n plus 1 plus L must be 3 h bar omega. Okay? There's no excitations in the individual clusters. That excitation must be in the relative motion of the pair. Okay? So how can I get 3 h bar omega from that? Well, I hope you'll agree there's 2 ways I can do it. I can put n is 2 and L is 1. That'll satisfy that. Or I can put L is 3 and n of 1. Okay? Okay? So this, if I've got this configuration, it's telling me the alpha and the triton have relative orbital angular momentum of 1 unit and big N is 2. Okay? And that says the wave function between those two clusters must have 1 node in it. Okay? The number of nodes is n minus 1. Okay? So if I'm going to generate a bound state to represent this, I need to generate a p-wave relative motion wave function bound state which has 1 node in it. Okay? Whereas this configuration here, the other possibility is that the two are in an F wave, L is equal to 3 units of angular momentum, in which case n must be 1, in which case there are no nodes in the relative motion wave function for that system. Okay? Okay, so what you see, though, is having taken my shell model-like wave function, decomposed it into clusters, looked where the quanta must be, and written this down, you'll see that the possibility is that I get 1 unit of relative orbital angular momentum. Remember, the triton spin is 1/2, and so that if I add 1/2 to this, I can get 2 states, one with 3/2 minus and one with 1/2 minus. Okay? Whereas in this configuration here, L is 3, so adding on the spin of the triton of 1/2, I can get 7/2 minus or 5/2 minus. Okay? So what this simple cluster model leads us to expect is that somewhere in the low energy spectrum of lithium-7 there should be these 4 states, okay, associated with the cluster structure of lithium-7. And if I want to describe these 4 states using a simple 2-body picture, I have to control the orbital angular momentum and the number of nodes in the wave function in this way for those particular configurations. Okay, so there it is again, and you'll see if you look at the physical spectrum of lithium-7, indeed we've got these 2 states down here. One is a 3/2 minus and one is a 1/2 minus. And so these 2 states are going to be associated with this sort of cluster configuration with a relative p wave and 1 node in the radial wave function. Physically, these states are somewhat higher, as you will see. This configuration, when you do it properly, when you don't do it in oscillators, but when we do it more realistically, these states have a higher energy in the lithium-7 system, but you see they're both there. There's a 7/2 minus and a 5/2 minus sitting up here, and they will be associated with this decomposition. So these will be L is equal to 3 states, and if I want to discuss these 3 states and model those 2 states, I should use a relative motion wave function involving 0 nodes in their relative motion wave function, because that is what is required by the Pauli principle in that case. Okay, so that's something else, okay? So if you're talking about nucleons, then we go to our favorite energy level scheme, and we put the nucleons into the levels in the appropriate way, and we figure out the quantum numbers of the bound state that we need to generate. If we've got clusters or more complicated configurations, we can get guidance by going to these very general simple oscillator rules, okay? And the advantage of doing this, rather than simply guessing, as I say, what we're doing is satisfying, when we put these particles into these orbitals and count quanta, what we're doing is satisfying the Pauli principle and making sure we're not putting particles in the right place. Okay, so I want to finish up with something that's going to emerge several times as we go through the course. Is this problem of scattering states, and in particular, if you've got a system in a bound state which then breaks up, we have this problem that we end up in a scattering state, and there is a scattering state for every energy, and so we end up with an infinite set of probable final states. Okay, so this is supposed to represent over here the sort of physics that we're talking about. Imagine we have a system such as beryllium-11 or carbon-19 or some of these exotic neutron-rich systems which have just one bound state, and then if you supply a little bit of energy, they become unbound, and then you can have some resonance states or other things happening in the continuum. Okay? So what I've represented here is that there is a threshold here. There's one bound state which has a binding energy of minus EB, and if I supply just that amount of energy, then the neutron and carbon-18 or neutron and beryllium-10 go into a scattering state, they become unbound, and then there's an infinite number of possible states sitting up here. Okay? Even for a given value of orbital angular momentum, there's an infinite number of states. Okay? And each orbital angular momentum you choose, there's an infinite number of states. Okay? And so there's our scattering state. We've written it down before. Okay? And if you try and normalize such scattering states, it's tough because they go on forever. And when you try and do the integral to large distances, it never stops. And if you try and integrate, do this normalization integral for scattering states, you get a delta function. Okay? So it's infinite when the two states have the same energy, and it's zero. They're orthogonal if they've got different energy. Okay? But this is a problem. Okay? And so I say there's a technique which is developed, which appears to be robust and useful, which is to say, we got all this infinite set of states with this partial wave, so let's say, let's divide up this infinite set of states into various intervals. Okay, let's say that all these low energy ones have some characteristic features. They're all low energy bins, okay, low energy states. Then there's another block here which we can say, let's consider this range of momenta delta k and group those together. Okay, and so instead of using these individual scattering wave functions here, what one does is take a linear superposition of states over some finite range delta k of momentum here. In other words, you take these wave functions, you can weight them if you want to, but imagine that number is just 1, and it's you produce a group, a superposition of scattering wave functions over some finite range of momenta here, and integrate them up. Okay? Okay, so don't worry about this thing G. Obviously, this is a general superposition, and if I take a linear combination of stuff, I can weight those different pieces by whatever weight function I would wish to. Okay, but a common choice of choosing G is just 1, and then it disappears from your life, and you don't have to worry about it anymore. Okay, but the cute thing about these wave functions, which are these linear superpositions, is that they behave just like real bound states. Okay. Namely, if I multiply two of these superpositions together and integrate them, I get 1 if they're the same, and I get 0 if they're different. So they produce an orthogonal and normalized set of states, just like bound states, just like excited states of a system. So in other words, we try and throw away this infinite set of states here, block stuff together, and then we end up with a finite set of states, which are called bins, and each of those has a well-defined normalization integral, and each of those is orthogonal to each other state. Okay, so that's another exercise. This may look complicated, but it's rather trivial. So again, it's another exercise that I'm asking you to think about this afternoon. You may not get there. If you're worried about it, just ask. Okay, I mean these problems aren't supposed to be something there which is a ball around your neck and you're supposed to do it independently. Please, if you have a go and you're genuinely, just ask. Think about it for 20 minutes first, but then please ask. Okay, so a technique, and again it's a two-body problem, so that's why it's here this morning. Okay, one way of treating this problem of an infinite number of states in low energy continuum is to make this trick where you sum stuff up. Okay, and so there's a little button there to an Excel spreadsheet, which I was going to show you what those states might look like, and but I hope you get the idea. Okay, let's not treat each of these infinite set of states individually. Let's just make some intelligent guesses about different blocks and treat these states in those blocks. Okay, so let me see if this will work and connect to this spreadsheet here. Okay, that's a funny scale. Can you? Don't know. Wasn't expecting it to be that size. How do I get rid of all this stuff at the top? Anybody know Excel this level? Can I get rid of all this rubbish at the top somehow? Down in the... Oh, there's this one. No. Oh, okay, let me just see if I can give you the basic idea over here. Okay, what I've done here is that I'm imagining what's over here is supposed to be a picture of these bin states. Okay, I start out with scattering states, and then I'm going to integrate over a range of these scattering states between some lower limit and an upper limit. Okay, so this is a range of k values, and what I've done is done an integral over the scattering states between this limit and this limit, and this is red, and over here there is a curve red showing you the behavior of this state. Okay, and what you might expect from your experience of taking wave functions that oscillate and producing a group by integrating a band of them is that the wider the interval of k I integrate over, the shorter the range the wave function will be, and the smaller the range of k, it's the uncertainty principle. Okay, if the range of k is small, the uncertainty in position is big, and if I increase the uncertainty in k by integrating over a wider range of momenta, the wave function should become more localized in space. Okay, but what I've done is I've got two bins here. Okay, one which is integrated between 0.55 and 0.65, and that's the blue curve. The red curve is integrated over this range here, and that's the red curve over here. Okay, and what you can see is that the normalization isn't 1 yet, because I haven't gone out far enough, but this goes from about 1 Fermi out to 100 Fermis, this full graph. Okay, so these functions remain reasonably long range, 100 Fermis. However, there's a finite number of them, and they are finite. Okay, and so the normalization of the red curve with integrating on this band is out to 100 Fermis is 93.6%. This is 93.8%, and down here is the orthogonality integral. If I ask, is this wave function and that wave function orthogonal to each other, i.e. you multiply them together and do the integral over all radial values, you get 0.0039. Okay? So all I'm showing you is that constructing these guys in this way produces wave functions which decay away in space over some finite range of radii and have essentially unit normalization, just like a bound state, and these two states are orthogonal to each other over there. Okay? And just to make the point that I said before, if I make this range bigger, if I make that 0.85 or something, if I knew the French keyboard, which is always interesting. Oh dear. Is it over here? How do you get? Okay, if I make that range bigger, as I told you, then the blue curve becomes more localized in space because the range of momentum is larger. The normalization goes up, and these two states remain orthogonal with each other. Okay, and the same way, if I make this bin wider, such that I encompass a wider range of momenta, if I can still do this, let me just increase this one. Okay, so let's make the integral on this bin wider. That means this becomes more localized in space. The normalization again goes up to 98% now, 0.98. So we've got almost a perfectly normalized two-body wave function, and the orthogonality between these states, as you see, is preserved. Okay, so this is the essential. I know there's too much going on here, but the essential feature of continuum bins is that what we do is take a continuum and say you can't do that. Let's divide up this continuum into intervals and try and use these representative wave functions in this way. Okay, and dealing with these guys is really essentially the same as dealing with bound states. Okay, because they have unit norm and they're orthogonal to each other, and so it becomes a couple channels problem of a standard sort. Yeah.
Have you now introduced some kind of time dependence now because you have a wave packet? Can you use this in time dependence?
There's no implicit time dependence. What we got is a stationary state theory here. Okay, where you've probably met this sort of idea before is producing wave packets out of. You take sine waves and they've got different frequencies or they've got different wave numbers, and when you take an integral over a set of these things you get a group, right? So that's in one dimension, and what you're doing there is you expand in a certain domain and you get a localization in the other domain, whether it's time and frequency or whatever. Okay, but what I'm doing here, I'm in the k, the momentum position of the pair. Okay, and so there's nothing explicitly time dependent in what I'm doing here. I'm just taking stationary oscillatory states and taking a linear superposition over some range of momenta to gain localization. Okay, it's the uncertainty principle, right? Obviously, in a calculation, you would like to make this as big as you can because you would like to have as few channels to deal with as you can. However, if there are resonances and other interesting things happen in this continuum, you may have to choose these bins. If something interesting is happening in this continuum, there's a resonance at some position, then we should put a small bin to discuss that resonance, and then perhaps if nothing very interesting has happened somewhere else, you can have a larger bin with more momenta which are more characteristic of a smoother part of the continuum. Okay, but say I think we can play with this some more later on to gain an idea. Okay, this is going to arise much later, but I say because today we're really talking about two-body problems and the sort of wave functions you can generate from a two-body problem, I think it's appropriate that it sits here at this level just to gain a simple idea of what's going on. No. Okay, so I think that's probably all I've got to say about continuum bins for the time being. I think that probably this might be my last slide for the morning, actually. This is about as complicated as we can get. Okay, so this afternoon, I say there's a little bit of algebra where I ask you to convince yourself of this. Okay, if we've got scattering states that look like that, it's all one-dimensional stuff with a simple delta function. One should be able to convince oneself that this integral here is 1 if these bins are different, and if they're the same, and is 0 if these bins are non-overlapping and different. Okay, and there's also a bit of code to construct these in a more realistic situation than the one I've just shown you on the spreadsheet. Okay, so let me just advertise something else that's coming. Can I just remind you that what we've learned about this S matrix, okay? The physical meaning of this S matrix. You may not be at one with it yet, but we'll get to love it as we go along, okay? We've seen that if we solve this radial equation, the interesting physics is this number, this set of complex numbers here, okay? And the physics is that this tells us how much stuff gets trapped in here and how much stuff escapes and comes back out here. Okay, so this is also relevant to stuff that we will do next week, where we discuss, for instance, fusion. Okay, so there's a well-known piece of physics which involves if two ions come together, what is the probability that they will come together and fuse and form a compound system? Okay, both in astrophysical environments and for nuclear structure purposes and for nuclear dynamics purposes, the fusion process is an interesting one. Okay, so if these are charged particles, then we know, as we've drawn earlier, there'll be a Coulomb barrier, and inside there will be an attractive pocket because of the attractive interactions between these two systems when they get to short distances. And so we have this problem that if I come in at an energy which is near the barrier, if I go over the top of the barrier, then these two can easily come together and fuse. If I come in at the top of the barrier, then there'll be quite a lot of reflection. And if I come in below the barrier, I've got to tunnel through this in order to come out. Okay? And I say barrier passing models of fusion make the assumption that if you come in at some energy and you get to short distances, there's a shaded bit there. If the two things come together at short distances, then they fuse together. Okay? And so what is then relevant is if I can calculate this quantity, which is how much stuff comes out, this comes from a solution of our Schrödinger equation. If I calculate that, it tells me how much stuff comes out. And so this quantity here tells me how much stuff did not come out. And so tells me about the amount of stuff that got in here and is describing the fusion process. Okay, so in addition, a very different piece of physics, which is the fusion of two nuclei, involves calculations of this same quantity that I've been talking about here this morning. Okay, so if I wanted to calculate the result for fusion, then the system can come in a whole range of angular momenta at some energy, and the fusion cross-section would be the cross-section due to each angular momentum that can be incident and contains nothing more than this term, this probability that the two come together and something interesting happens, and this is the probability that they get captured and produces fusion. Okay, so this quantity S, I say we need it because it enters many, many problems. A basic physical property that tells you bring stuff together, does the stuff come out again or does it stay reacted at short distances? And that's relevant to a lot of reacting systems. Okay, so this afternoon we're going to do some simple stuff. Okay, so I've talked about bound states. I would like us to work out some bound states in potential wells, to look what the wave functions look like, to understand these single particle quantum numbers. I've got various little scattering bits and pieces that you can play with, but what I'm interested in here is what the S matrix look like. As I told you, the modulus of the S matrix is supposed to be absorbed in the small partial waves and then go to 1 at large systems. Okay, we can calculate phase shifts, so we can look for resonant phenomena. We can look for phase shifts that are going through 90 degrees, and we can look at what the cross-section looks like due to the potential which is producing those phase shifts, and we can see whether we get this bright Wigner type bump in the reaction cross-section and match that with what is happening in the phase shift at low energies and such like. Okay, so there's various things we can do by looking at the scattering of two particles at low energies in real and complex potentials. Bins, I've talked about bins here at the end, taking linear superpositions of scattering states to produce these pseudo bound state systems. We've talked about the Hartree-Fock as well to calculate densities, which we'll use later on. And so if you want to run this thing through and look at your favorite nucleus or see what the mean field tells you for sulfur 44 or silicon 42, or take a nucleus, want to see what it predicts for the densities, this is a simple way of getting us started in that simple model, the mean field. Okay? I think that's it for this morning, I think. And I say what I hope is that we kick-started things, and Team Ferrari will get most of the way to the end of the problem sheet this afternoon. Okay? Are there questions? There are no questions. You're hungry. Can't be hungry after sitting there all morning. You haven't done anything. I think we need 4 circuits of the room or something before we go off for lunch. Okay, right. So as I say, the philosophy is later on, Philomena and Antonio and others are going to introduce you to more sophisticated codes that do clever things. And sitting underneath these codes will be all sorts of stuff that you need to introduce, okay, to do DWBA and other things, okay. And but what those codes are going to be doing is calculating distorted waves, bound states, bins, all this stuff, okay. So what I'm interested in day one is that when you dial up that particular option in the code that you want bound state, number of nodes, clusters, how many when you're dialing up these various inputs, you should know what the consequences of putting a 2 or a 3 in a certain position are, okay? Because it's very easy to get a data set that seems to work, produces something that looks vaguely sensible, and then just twiddle the numbers. But unless you understand what the inputs are, it's a death trap. Okay, so please have a go at these things. Really understand what's happening underneath the bonnet, so to speak. Make sure that you know what these various dials on the more sophisticated codes are doing for you. Okay, that's the philosophy here today. Some of it you've done before, some of it you haven't, but it's all intended to make you better educated later on when you start doing more sophisticated things. Okay. So